Okay, so this is a very strange experience for me. Thanks for letting me speak, and I don't see you guys, but I hope you're having a nice conference. Can I start?
Can you give me 1 second? Everyone is coming back into the room now, so.
Well, they were probably having fun. Now they're gonna come and be tortured by.
Okay, the next speaker is Grigor Sargsyan from the Polish Academy of Science, and he will talk about hot mice as a bridge between determinacy, forcing axioms, and infintary combinatorics. Okay, Grigor.
Okay, thank you. So let me first. It would be nice if I could see you, but I don't see you. So thanks for letting me speak, and thanks for sticking around. I guess maybe I cannot see because not many people are there. Okay, let me apologize first because it was very hectic times and it was very difficult to concentrate on this particular slides. So the title is inspired by the title of the conference. It seems like too many areas are in one conference, and I thought maybe I can explain how hot mice play a role in several areas of setting. Okay, so what are hot mice? You probably already know. They're used to represent hot of determinacy models as fine structured objects. I'm sure John already told you everything about them. They've been used to solve old problems asked by the Cabal group, for example, how to satisfies GCH, out of a determinacy model. They've been also used in Kolmar induction applications to calculate low bounds. And for example, here is a theorem, which is a recent theorem. The following two theories are equiconsistent. CH plus there is an omega-1 density on omega-1, and ZF plus ADR plus theta is regular. So the 2 to 1 is a theorem of Wooden. I guess reversed. 1 to 2 is a recent theorem. Okay. What is a hot mouse? Let me just remind you. Basically, it's a fine structural thing that's built by from an extended sequence and a strategy. Sigma. The strategy sigma is internal to P. So I'm a hot pre-mouse. It's a first order statement, and it in particular implies that the universe is iterable, right? So you can just basically think, when I say V is a hot mouse, you can think of it as just basically V has an iteration strategy. I'm not gonna care too much about the type of fine structure it has. What's important is that it's iterable. V thinks that it's iterable. Okay, so hot mouse itself is just an iterable hot mouse. All right, so that's all I will, I guess one more slide about hot mice. Historically, I mean, I don't know if this history is correct because there was history before my time, but when I got into model theory, this seemed to be just something very technical that's relevant only to model theory. But then I think now it's clear to me that it's relevant to other things as well. And I like to demonstrate that it is relevant to other subjects. Okay, so that's all about hot mice. So the first problem I like to consider is the cofinality data problem. UB is the set of all university pair sets. Can you please stop me because it's a very strange experience to give a talk this way. I'm not used to it as well. Okay, if I'm going too fast, please stop me. Yeah. Okay, so data UB is the supremum of all alpha such that there is a surjection from real sum to alpha, and so that the associated trivial ordering is UB. Okay, if under certain closure properties, right? If L of UBR does not have new sets of reals, then it's just simply theta of L of UBR. Okay, so assume proper class of Wooden cardinals are the natural extensions of ZFC that decide the value of theta UB or cofinality of theta UB. And in particular, you would like to know if MM++ decides this value, right? There's a recent theorem of Wooden, and I'm not 100% sure if I got the hypothesis correctly. I think I did. If you assume MM++, then and assume class of Wooden cardinals, then UB is definable over H omega 3, which means these are definable, very local, very low level definable. In general, when you say a set is UB, then you say, well, for every cardinal kappa, right? So it's a very global property. But the theorem says that it's actually very local. And so to me, I don't want to inject this feeling to anybody else, but to me, this, if you cannot decide it in the extensions of MM++, that to me, that seems like a problem for MM++. That's a very natural question, which MM++ or its extensions would not decide. Okay, so what can we say about this? Well, first of all, in the standard model of MM++, theta UB is less than omega-3. And so the only possible cofinalities are omega-1 and omega-2. It's easy to see that cof omega is ruled out, right? Because you can always put omega many UB sets together. All right. So in general, studying the UB sets, it's the best environment for that, in my opinion, is Sealing. So Sealing, what is Sealing? Well, it's saying that you have an embedding from the ground model UB sets into the UB sets you obtain in the generic extension. And it has these two extra clauses. You assume wooden cardinals just because, when you have wooden cardinals, UB sets are much nicer. Point two, that's irrelevant. If you assume large cardinals, then point two is irrelevant. It will just follow for 1 and 3, basically. Okay, so Sealing is basically saying that if you force, go to VG, then after do another one, VGH, then you have an embedding, but the embedding is completely, is determined on the sets of reals, right? So maybe above you can do different things, but as far as sets of reals go, that's what you can do. Okay, so Sealing tells you that the theory of UB sets cannot be changed. Okay, so they become canonical objects. Okay, so you would like to study this problem on the Sealing. What can we say? Well, each of the possible cofinalities, I mean, omega-4 is probably also a possible cofinality, but that's a big open problem. So I don't have anything to say about that one. But you can have the other 3 cofinalities consistent. Right, so Sealing does not tell you what the cofinality should be. The cofinality omega-1 case, the other 2 are exactly what they are, but the omega-1 case, you want to make that a bit more precise, because it doesn't quite make sense to say what. I mean, when we say, at least when I say cofinality of theta UB is omega-1, I mean something a little bit stronger. So here's what I mean. You want to say that the cofinality theta UB is omega-1, but you also want to say that it never changes as long as you keep omega-1 the same. So if you go to a generic extension in which omega-1, your new omega-1 is the same as the old omega-1, then the old UB sets are cofinal, wedge cofinal in the new UB sets, right? So you didn't create, basically this is saying you cannot create new universally bare sets by stationary self-preserving forcing or forcing self-preserving one. Okay, so here in the first case, in clause 1, it's that theory that I mean is consistent, not the. Okay, so what are the models? So the first one is for cof theta is omega-1. Suppose V is a hot primaus, and there is a class of wooden cardinals, and kappa is a strong cardinal. Okay, so let lambda be the least inaccessible cardinal above kappa and just make it omega-1. Okay, then you get cofinality theta is omega-1. So again, in the strong sense, that means that if you do further forcing that preserves omega-1, you can add reals, but to preserve omega-1, then you have the old UB sets cofinal, wedge cofinal UB sets. And this was inspired by an argument of Wooden. Okay, so Wooden outlined to me an argument. Sorry, what was that? Yeah, so he said that something like this can be done with his notion of hot mice with long extinguished. Yeah, but I don't know the proof. Okay, so let me tell you a little bit about how one would prove something like this. Okay, so the G is collapsing lambda to be omega 1, right? Lambda is the least inaccessible cardinal number. Okay, so you do that, you get ceiling. That's the theorem that Nam and myself proved. The ceiling is actually, that's already done. The rest is basically, you want to prove, what one wants to prove is that V up to lambda is universal now with respect to countable mice, countable least branch mice. For that to work, universal means it wins the coiteration with anything that's countable, right, in less than omega 1 steps. And that kind of comparison arguments cannot be done by the comparison arguments that John developed in this book. So you have to do this different type of comparison argument. But it all works out. So you end up having that V up to lambda is universal. And then, I mean, then it's an exercise in homogeneously Susslin sets, basically. The way the proof proceeds, I didn't put it on the slides, but the way the proof proceeds is you imagine you have a universally bare set, but you have class of wooden cardinals. So you can take a countable substructure of V, which has those measures, the homogeneity measures point each one in the whole, not the whole system, yeah. But then you can, but then the iteration strategy of the countable substructure will be above the new UB set that you introduced, page above. But then, and then you do the comparison. So if you do comparison, V up to lambda wins. But if V up to lambda wins, that means one of the old strategies, right, is stronger than your new UB set. So that's how basically it goes. The key technical thing is to prove this comparison argument. Okay. So that's the proof for that. For top theta is omega 1. Okay. How we get cos theta is omega 3. Well, I don't know if there is another way of doing it. The only way I could see is doing it over determinacy. Okay, so we start with the V is a hot mouse. Oh, this came up when Matteo was visiting Inan's class last fall. Okay, so we start with the hot mouse. Then we have a class of wooden cardinals, and there are two strong cardinals. Okay, so now we do, we take we compute the iterate V lambda. So compute all the iterates of less than lambda length iterates of V up to lambda, which converges to HUD of the derived model with lambda, right? So you do that. Okay, then we compute the derived model. Basically 3K is the derived model, but you put M in there. Well, M is that direct limit. Okay, then we want to force. Okay, so we will force with Pmax and then add point subset to omega 3. You'll get ceiling and you'll get theta UB is omega 3. You get theta UB is omega 3 because you don't introduce new university pair sets. You get ceiling because of the theorem that I mentioned that Nam and I proved. And K satisfies ADR, that's another thing that you have to verify. Okay, I don't know if this is possible to do without hot mice. So it's a question one can think about. All right, should I, okay, let me, oops, see. Well, this one is easy, right? Because you, if you do countably closed forcing, and you have class of wooden cardinals, then you will not introduce new homogeneity systems, which means you will not introduce new university pair sets. And so you can just collapse omega 3 to omega 2, but you could also repeat whatever I wrote here, except now you change the forcing to this one. You force with, you well order the reals, and then you add a point subset to omega 2. By the same proof, basically, you get ceiling plus theta UB equals omega 2. Okay, so ceiling doesn't say anything about proportionality of theta, but I guess the way we proved the three theorems, I would just, let me go over them again just to make sure. So first one is, you have a hot mouse. Why did I restrict? I mean, here, for this one, we need this comparison argument. I don't know how to prove comparison argument all the way well, we don't know how to create the hard mice all the way, right? So if you build stronger hard mice, then the same proof will basically work for anything, for any theory, right? So if, in particular, if you want to get, if you want to do MM++ ceiling plus cofinality theta is omega-1, you just take that template. Once you have the hard mice themselves that will give you MM++, then you take the template and it's supposed to give you the proof for ceiling plus cofinality theta in P. Okay, so if inner model theory succeeds, so if you have a hard mouse with super compacts and etc., then you should be able to get ceiling plus cofinality theta is omega-1. Omega-2 and omega-3, well, let's talk about omega-3. You could do the same thing that I did, right? What did I do? I just took an M, I took a V, which was a hard mouse, and took the direct limit of 4 less than lambda each rates of V. Well, if you have a V satisfying a super compact, you could do the same proof and you'll get theta in V is omega-3. So this will also be possible. Okay, so this seems like a test question for model theory, and I think to me it's a bad news for MM++ if it's true. But I don't want to insist. You guys can be paid. It is bad news. Okay, so the next topic is: did I go too fast?
Yes.
Okay, so the next topic is Berkeley cardinals. And let's say kappa is called a lambda Berkeley cardinal if for every transitive M of size less than lambda, and for every alpha, there is an elementary embedding from M to M with critical point greater than alpha. Okay. Okay, there's a more general notion when you say kappa is a Berkeley cardinal. Oh, sorry, I meant kappa should be contained inside M, right? So this is for every transitive M that contains kappa and has size less than lambda. And for every alpha less than kappa, there is, yeah. Ooh, and critical point is less than kappa. Oof. So there are two typos. M should contain kappa and the critical point should be less than kappa. Okay. I guess there is the more general version when you say, when you don't demand that M to be well ordered, right? So for any transitive structure that contains kappa, there is an embedding from M to M with critical point bigger than alpha and less than kappa. Okay, so kappa is odd Berkeley cardinal. If for every lambda, kappa is a lambda Berkeley cardinal. Kappa is a hard Berkeley cardinal if closed one above holds for all M in hard. And of course, Margaria Kohler wouldn't prove that there is a hard Berkeley cardinal, then the hard conjecture fails. So that's why it's not interesting. Okay. So Berkeley cardinals on the AD. Well, there is always famous theorem that omega-1 is omega-2 Berkeley. Well, we don't usually state it that way, right? So that's because every subset of omega-1 is constructible from a real, and every real has a sharp. So any set of any transitive structure of size omega less than omega-2 is constructed from a real, so you will get an embedding from it to itself. Yeah. Okay. So again, with dark blue, we showed that on the AD plus, omega-1 is theta Berkeley. In fact, omega-1 is club theta Berkeley, so the set of critical points below omega-1 is a club subset of omega-1. Yeah. Okay, so in fact, you can prove that every Suslin cardinal is an omega club theta Berkeley cardinal. So we can also prove things like omega-2 is a Berkeley cardinal, delta 1, 4 is a Berkeley cardinal. So the successors of projective Suslin cardinals are also Berkeley cardinals, but I was not able to, I think we were not able to verify that the successor of arbitrary regular Suslin cardinal is a theta Berkeley cardinal. Okay, so SUM80 plus, then Gabe was in Gdansk a few weeks ago, and we were thinking that theta, well, we thought we could show that theta is a limit of theta Berkeley cardinals. Well, one has to think. So this is one of those conjectures that you think you have the proof. It's not the conjecture. like the first conjecture, I don't have any the proof, but this one we seem to have the proof. Okay, so what is the key idea behind the proof? Well, suppose we have a mouse pair. Kappa is the least measurable cardinal of P, and E is the total extended in P whose critical point is kappa. So it's the least, it has mutual order 0 at this measure. Okay, so what do? We take the ultra power, we let lambda be sigma Q. So the strategy of Q. Then we let M infinity P sigma kappa be the direct limit of all countable iterates of P sigma that are above kappa, right? So we're gonna fix kappa and iterate above. Just fix kappa, right? That in the, like if you do in L of R, then and P sigma was basically M omega, then that would iterate to odd over P up to where the measure is indexed, where E is indexed, right? Okay, so we do the same thing for Q, and then you can see that you could generate an embedding. So the ultra power embedding generates an embedding between the direct limits. And to prove that, you use the full normalization technique that Benny and Farmer and John developed recently. Okay, so I don't know how to do without full normalization in Simpson distribution. Basically, when you iterate P, you can, when you iterate P above kappa, then take the ultra power of kappa when at the final iterate, that becomes an iterate of Q. And this way you can embed P's direct limit into Q's direct limit. So why does this give you Berkeley cardinal? Well, imagine you had some M which you were trying to prove and produce an embedding from it to itself. That M is ordinal definable from some. Let's say we are doing an L of R, right? So it would be ordinal definable from some real, while pica P, which would converge, whose direct limit will converge to hard over that real, minimize your M, right? So it should be the least ordinal definable thing for which there is no embedding from it to itself. And then this embedding K that is defined in 4, that embedding will fix it. Okay. Because of definability. This M infinity P sigma kappa is really hard relative to something. And the other one is also hard. And K will fix this M for which you were trying to produce the Berkeley embedding. Right. Okay. So that's the Berkeley problems. Now I feel like I'm going extremely fast.
Yes.
Should I slow down or?
Yes.
But can you ask me questions? Because I don't know how to do it. No one's talking to me. Where should I slow down? Okay. Should I say more about this proof?
Yes.
All right. Let me just repeat what I said. Yes, imagine you were trying to do this in L of R, right? Okay, so we're trying to prove, that's the definition of Berkeley cardinal, right? Trying to produce an embedding from some M to itself. Okay, so now take the least M for which there is no embedding from it to itself. Okay? All right, so that if now find a hard limit that absorbs that M. So M infinity P sigma kappa, that's a hard limit, which is going to have M in it. Right? Now that M is definable in M infinity P sigma kappa as the least thing which violates the Berkeleyness in its own derived model. Right? So M infinity P sigma kappa says this M is the least thing such that when I do my derived model, it does not have an embedding from it to itself with critical point less than omega 1, so that you can just write down that formula. Okay, so K of M must be M itself because you picked M, you minimized M in the ambient determinacy model, not inside hub, right? So K of M is M. And then Why is there a critical point less than omega-1? Well, because the critical point is given by pi mu, right? So the least measurable of P is the critical point, which is smaller than omega-1. Why do you get club? Well, you could have iterated as many times as you want, right? So, okay, so that's the proof. It's not, this one is just to point out that this could become a way of producing Berkeley cardinals in the ZFC context. So we can assume AD in LOR, then do Pmax. Well, Pmax is homogeneous, so you didn't add any new OD, I mean, well-ordered sets, which are basically subsets of ordinals which are definable from a real. Okay, so that means you already had a Berkeley-like embedding for such things, and so they will stay Berkeley embeddings in the Pmax extension. And okay, so here's a conjecture that AD plus omega-1 is an odd Berkeley cardinal is consistent relative to large cardinals. In the second part of the talk, I will provide a guess for where they should hold. It's again a speculation, but I think this is probably true. And of course, I'm less sure about this one because I don't know which model will have the first one. But if you have the first one, then maybe you should some Pmax, some extension of Pmax will allow you to force and get omega-1 subgroup. Right, so this is a variant of the question whether you can force Feynman's maximum over determinants. Right? And I think it's a good place to stop because I have two more topics. And what time am I supposed to stop before the break?
4 p.m.
4 p.m. I thought it was 3:45. I had to stop.
Yes, but we started at 3:15. But anyway.
So how about I just go on and then we will finish early? Is that okay with people?
Yes.
Okay, good. Because it seems like I'm all right. Okay, so I could have made more slides, but I thought that I already have way more than I could cover. Okay. All right, so then the next topic is forcing instances of Martin's maximum over determinacy. I have to introduce the models, the Nairian models. Assume ADR for an ordinal gamma less than theta. The Nairian model at gamma is the following model. So first, let X gamma be the union of hot up to beta countable sequences from hot up to beta. Well, the reason you want to do it this way is because gamma could have cofinality omega, and so you don't want to take cofinal sub omega sequences, but just the multiples. Okay, so the first one is the minus version, which is just L gamma X gamma. And one key, it will not come up in this talk, but when I write that, what I mean is the ordinal height of N gamma minus is gamma. Okay, so the second one is L of this. Right? And the third one is the plus version, which is hot X gamma. Right, so the first one is you build up to gamma, so the ordinal height is gamma. The second one is L of countable sequences from hot up to gamma. And the last one is the full ordinal definable set, the full hot relative to X. By the way, I don't know if I got the notation correctly. You're allowed to use parameters from X gamma, yeah? So hot sub X gamma is allowed to use parameters from it. Okay, so let's say gamma is a stable point if we let kappa to be the theta of M plus gamma, right? Then, okay, so you want to say M plus gamma is a model of ADR. And you want to say that you didn't introduce, if you build the model up to kappa, then that will already have all sets of reals, right? Okay, so a priori, gamma could be bigger than kappa, right? So putting the countable sequences from gamma do not create new sets of reals of weight rank less than kappa, right? So the picture looks kind of like, okay, so the way I wrote it, it's you have gamma and then you go down, but you can think of it as upside down. So you go to kappa, you have all sets of reals of weight rank kappa, but then when you start adding countable sequences from bigger ordinals, no new ordinal definable set of reals appears from those countable sequences, right? Okay. Okay. So that's what stable means. So we say kappa is a Solovay cardinal if for every nu less than kappa, there is no ODE surjection from the power set of nu onto kappa. Right, so these are the points in the Solovay sequence. Okay, now if you assume 80 plus, so John proved this, I think it might be in his book, I don't know. So if you assume 80 plus HPC plus, and also assume B equals L of P of R, suppose delta is a Solovay cardinal such that there is a largest Solovay cardinal less than delta, and delta is a limit of wooden cardinals in HUD. Okay, so by a theorem of wooden, delta itself is also wooden, yeah, in HUD. So you have a wooden limit of woodens inside HUD. Delta is woodens inside HUD, and you have the largest. So this is like the LSA type of situation. Okay, so then delta is stable point. What that means is that in the traditional terminology, you'll have theta alpha, that's kappa. That's the largest Solovay cardinal less than delta, theta alpha. Theta alpha plus 1 is delta. And now you do HUD of countable sequences from theta alpha plus 1, right? And that does not create any new sets of reals of weight rank theta alpha. Can I just see if we see? Boban is in 629. I'm just using this computer. Sorry. Okay, then in the same situation, you'll get actually if you do the minus version, so you cut the universe at delta, then wouldn't show that you get a model of Z. Okay. Right. Any? Okay. All right. So this is a little bit technical. So we let hypo eta delta xi be the following statement. V is a HUD mouse. Eta is an inaccessible limit of wooden cardinals. Delta is a wooden cardinal such that no delta prime less than delta is strong past delta. So delta is a cut point, right? Xi is either a less than delta strong cardinal or it's a limit of the less than delta strong cardinals. Right? So you have a HUD mouse, you have, oh, I forgot to say that eta is bigger than delta. So eta is bigger than delta, delta is bigger than xi. So eta is inaccessible limit of wooden cardinals, it's bigger than delta. Delta is a wooden cardinal, which is a cut point. So nothing below is strong past delta. Xi is either less than delta strong cardinal or a limit of less than delta strong cardinal. And xi is a limit of wooden cardinals. Okay. So if you're familiar with the HUD mice, this is kind of in the LSA situation, right? When you have a wooden, a strong to the wooden, the least strong to the wooden is a limit of woodens itself. So it's in the LSA type of situation. Okay, so it's a minimality assumption. So no xi prime less than xi is a measurable limit of less than delta strong cardinals. Right? Just a minimality assumption. Okay, so that's the hypo. Basically, let me just reiterate. Eta is an inaccessible limit of wooden cardinals. It's bigger than delta. Delta is just a cut point in wooden. Xi is either a strong less than delta strong cardinal or limit of less than delta strong cardinals. Xi is a limit of wooden cardinals. And no xi prime is a measurable limit of less than delta strong cardinals. So it's a minimality assumption. Okay. So assume this hypothesis, which probably already forgot. But okay. So now we remember eta is a limit of woodens. So if I do symmetric clubs, I can compute the derived model. So M, which is L of U B G R G, M will be a model of determinacy. And you're in a hot mouse situation, so you always get a model of ADR. So M is actually a model of ADR plus theta is regular, right? Okay, so now we do the direct limit construction. We iterate V up to eta by look at all the less than eta iterates of V up to eta. That's a directed system. From the direct limit, that gives you H, which is the hard of the derived model, right? Okay, so M is the determinacy model. Now, we had a notion of stability, Solovay cardinal, etc. inside determinacy models. So when I say in M, that I mean apply that notion of stability inside M, right? So pi xi is a stable point, which meant that if you compute this Nairian model at pi xi, that will not introduce new sets of reals at its theta, right? So its theta will be smaller, it will be bigger, and countable sequences will not introduce new sets of reals, smaller ratio. Okay, if in addition, you also know that psi is an inaccessible limit of less than the strong cardinals, then you actually get that ZF, you actually get ZF. So you didn't need to, in Wooden's theorem, you had to go all the way to the top Wooden to get model of ZF. Here you get an inaccessible limit of less than the strong cardinal, so much earlier. And of course, you get omega 1 is super compact just because under ADR, omega 1 is super compact, and by Wooden's theorem, those measures are always unique, so they're ordinally definable, and they go down to n. What I would like to point out in this theorem, you see the hypo. In the hypo, we are not assuming that V is small. In the hypo, we are assuming that psi is small. So V could have any large cardinal whatsoever. We're just saying that psi itself is small, right? So V could be as big, it could have supercompacts, it doesn't matter. The psi is small, not V. And so the theorem is true no matter what large cardinals V has. Right. Okay. So that's that. All right, so what is the theorem? The statement that there is an eta delta psi such that the hypo is true, plus psi is an inaccessible limit of less than delta strong cardinals, which is what we needed to get the ZF thingy. That's consistency-wise weaker than a Wooden cardinal that's a limit of Wooden cardinals. Okay, which means, which just if you compose it with the theorem in the previous slide, what that says is that in theory, ADR plus theta is a regular cardinal plus omega 1 is super compact is weaker than a Wooden cardinal that's a limit of Wooden cardinals. Okay, so
how much weaker? What is there some weaker large cardinal that you can give a name for that is a better upper bound?
Oh, no, that's it. No, these things go through divergent models. I don't really know how it would. Maybe if one does mouse set proof, yeah, probably like some strongs reflecting strongs would be higher. But I cannot vouch for it. I think it would be the region of strongs reflecting strongs. In general, the producing
some approximation to a Wooden limit of Woodens where the top cardinal is not Wooden with respect to all sets. Is that it?
No, I mean even weaker than that. Just a strong reflecting proper class of Wooden cardinals, proper class of strongs, and proper class of strongs reflecting strongs. So I think it's weaker than what you said. Basically, alternating chain of length 2, where the critical points are limits of Woodens, yeah? So if you can take an ultra power, then come back to the original model with the overlapping extender like that. And the critical points of the extenders themselves are limits of woodenness. I think that should already be stronger than this, but I don't know. Because the reason I said that is because I think Mauset proof goes through. So I think you can prove Mauset from this below this hypothesis. So okay. So what's next? Okay, the reason you would like to consider this, I mean, I think they're nice in just by themselves in the determinacy models, but you would like to force things over them, because that was my original motivation, was really the forcing side. Okay, so you let's assume that the hypo, so we're assuming eta is a limit of woodens, right? V is a hard mouse, eta is a limit of woodens, delta is a cut point wooden. Now what is psi? Psi is the n plus first less than delta strong cardinal, right? So there are n plus one many strong cardinals below, less than delta strong cardinals. And they're all limits of woodens, right? That's the thing that doesn't show up on the slides. So each of these n plus one strong cardinals, less than delta strong cardinals, are limits of woodens. Whoa. All right, so we do whoa. Okay, so we do the direct limit like we did before at eta, right? So this is the h comes from the previous slide. So you do the direct limit of all iterates of v up to eta. So that's what h is. It's the heart of the derived model at eta. Okay, so kappa i's will be the images of the strong cardinals, right? So psi pi psi will be kappa n. All right, now we collapse. Okay, so we do the derived model. Then in M, kappa 0 becomes the theta of the Nairian model of psi, right? So n psi, remember what it was. It's, you look at h up to psi, take all the countable sequences from that, and do L of this. Okay, so we have the kappa I plus 1. So the next strong is the successor cardinal of n psi. Right, so the first n strongs are just successors of each other. Okay, and then the forcing part, if you start with Pmax and then add coin subsets to each one of these kappas, you'll end up with a model in which successive squares fail. Right, and MM++C portion is a theorem of Wooden, comes from his big book, so we didn't do that. And the I equals 0 case was done a long time ago. So if I equals 0, you don't need any Nairian models. It's just n basically. It's just n. Then you have just kappa 0. So you work with your n psi is L offsets of reals of wage rank less than 0. Right? Okay, so the point is, if you have this hypothesis, you can force the failure of successive squares, and failure of successive squares is a consequence of Martin's maximum for posets of size bigger than continuum. So this is, if you want to get this from Martin's maximum, you need to assume more than C, MM plus C, right? Okay, so that's the point. So I would think this is a possibility, which I don't know if it's possible, but I think seems extremely intriguing. If you now, instead of, okay, we fixed the first n finite number of strongs. What if you do omega plus 1 many strongs? Can you force failure of squares sub Aleph omega? There is a technical problem. The problem being, here we are doing this iteration. Yeah, okay, but that's just a finite iteration. If you're at omega, then you have to do, I mean, and then you have to take limits. You probably have to take inverse limits to keep your poset omega closed. Okay, but then the poset becomes way too big. So forcing choice will become an issue, yeah? but maybe it's possible to resolve. I don't know. Yeah, was there a question?
What's the upper bound on hypo again for this hypo for this theorem? What's your consistency strike upper bound?
This term, I mean, it's again wooden limit of woodens, but I don't. I think one can reduce to strongs reflecting strong, class of woodens, class of strongs, class of strong reflecting strongs. I think it should. Some version of hyper strongness will do it. I think.
And it's not an iterable model with this approximation. It's not. It's just the large cardinal hypothesis. You don't have an iterability hypothesis. Is that right?
Yes. So the mouse, one needs to get the hard mouse, right? So if you, what is? I guess maybe I misunderstood the question. What is the mouse? Pure mouse, the LOV mouse, not the hard mouse. What is the pure LOV mouse that would give this type of hard mouse? I think if one starts with the pure LOV mouse, which has kappa, class of woodens, class of strongs, and class of strongs reflecting strongs, then one can build a hard mouse of this that satisfies the hypothesis of this thing.
Is that going through divergent models somehow?
Oh, no, this will be just a mouse set proof. Okay. You'll try to recover the generator for the derived model inside itself, and then do calculations. Show that if it was too small, yeah. That sort of argument.
And if you do this at aleph omega, you've destroyed the ideology of.
With aleph, yeah. If you okay, so I don't know how to force it. Maybe this theory is much stronger than wooden limit of woodens. In which case, it's not possible, right? In which case, it means that something very combinatorial goes wrong with forcing choice. So. But at any rate, I mean, I think people who are better than me at forcing should look at this problem. It could reduce the hypothesis much, below wooden limit of woodens. Okay. So you would like to force it over maybe. The second challenge, well, can you actually produce a model of the failure of consecutive squares from just a wooden kernel that's a limit of wooden kernels? And I guess the question here is whether one can do it from large kernels themselves rather than go to some determinacy model and then force over it, whether you can start from a super strong, do the sort of some traditional large kernel forcing and get the result. I know that you can do for subcompacts, but I don't know if one can even reduce it lower. Yeah? Okay, and the
failure of a square round. Oh, it is square round.
The round and the
that's
sub.
That's the question. Sorry. Oh, it is on the top.
Yes, it's consistency-wise weaker, but the question is asking whether it's possible to do by just forcing over a model of ZFC. Not because the way we did it, I mean, we went to the derived model, we built some determinacy model, and then forced over that. It could be that it's just not possible to do with just large kernels, right? Am I getting the question correctly?
Right. You show the consistency from a much weaker hypothesis. Right. So if you had the omega conjecture and a super strong cardinal, obviously you can force it.
Right.
Omega consistent.
Right.
Your other argument. So maybe you mean something else? I mean, are you showing that bottom line is relatively weak from large cardinal hypotheses?
This line?
Yes.
Yeah, it's weaker than wooden cardinal. That's a limit of wooden cardinals.
So it's omega consistent from cardinals much less than super strong. So if you had the omega conjecture, you can force it.
But can you do it
So
over any model?
What?
If that's super strong?
Any omega consistent statement can be forced.
Well, I mean, it can be forced from
So it's
something.
a challenge
It can be
to
forced
find. Okay. Okay.
Yeah, okay? I don't. This is a miscommunication. I don't really. Did I write something? I mean, if the theory is weaker, then why from some large kernel you have some proof that it's weaker. Doesn't mean you forced it, right? Okay. Can I go on?
Yes.
Okay.
I guess the question is, should we take a break before? How long do you have in your slides?
Okay, maybe like another 25 minutes, something like that.
So should we take a 10-minute break?
Okay.
Okay, let's take a 10-minute break and we'll come back about 4:15, maybe. Let's thank Grigor.